For this lesson, we're going to talk about scientific notation. That is any number of the form a times 10 to the power of n. A has to be between 1 and 10, and n is an integer. So if we first look at 5 times 10 to the fourth, what this means is we're going to take 5 and we're going to move the decimal point 4 places to the right. So I'll write 5 with a decimal point. I'll add in 4 zeros. So the number has to get bigger, and it goes 1, 2, 3, 4 places this way. So this number is really a 5 followed by 4 zeros, or 50,000. So scientific notation is good if you want to express a large number, but it's also good if you want to write a number that's very small, like 1.6 times 10 to the negative 7. This means we're going to take 1.6, but the decimal point is going to go to the left because we're dividing by 10 as opposed to the right. So I'll put in 7 zeros, and I know the decimal point has to end at this location here. So that's 1, 2, 3, 4, 5, 6, 7. And I put a 0 on the other side of the decimal point. So this is really 0.000000016. For example 1, I want to write these numbers in scientific notation. For part A, I have to choose my value for A, which is going to be 8, and it's going to be times 10 to a power. And that power is just going to be how many zeros appear in the number. So there's a total of 7, so that's going to be my value for n. So what this would do is take the decimal point after 8 and move it 7 places to the right because we're multiplying by 10. Now if we compare this to part B, so I have to decide again what the value for A has to be. And it has to be something between 1 and 10. So I'm going to use 7.5. That's definitely greater than 1 and less than 10. And I'm going to multiply by 10 to a power. That power has got to be a negative number because the value should be getting smaller. Now this is not just counting the number of zeros that appear, but how many times the decimal point has to move. So there's 3 zeros, but we have to actually go one further to be between the 7 and the 5. So in this case, n is going to be equal to negative 4. And you can check by going in the other direction. Like, okay, if I move the decimal point 4 places to the left, it would only give me 3 zeros, so it does match up with the value given in B. For parts C and D, something a little bit different happens here. These numbers kind of look like they're in scientific notation, but the problem is, here you have 17, but that's not going to work for A, just because this is greater than 10. And likewise, in part D, it looks like A is equal to 0.83, but the problem here is that number is less than 1. You can always write the number so it's between 1 and 10. So maybe to figure this one out, for part C, I'm going to just write 17 with a total of 1, 2, 3, 4, 5 zeros after it. And then decide, well, how can I now put this back into scientific notation? So it'll turn out that you have to move the decimal point 1, 2, 3, 4, 5, but now an extra 1 to get a number between 1 and 10. So this is going to be 1.7 times 10 to the power of 6. So I see the adjustment that we have to make. What you need to do is place the decimal between the 1 and the 7 to get 1.7, but this means you're now going 1 further. So that's why we went from n equals 5 to n is equal to 6. So likewise for part D, I don't want to use 0.83, that won't work. Instead, I want to use, I think 8.3 would be good. So I'll write this number out. That's going to be 0. Now I have to put in 1, 2, 3, 4 zeros, and then I'll write the 8.3 because the decimal point started to the left of 8. But now if I want to get 8.3, the decimal has to go back now 5 places. So that is going to be times 10 to the negative 5th. So in both C and D, here we had to increase the exponent because we had to go 1 further. Same thing happened in part D. So now both of these numbers listed here are definitely in scientific notation, and that's because we wanted the value for a to be between 1 and 10. For example 2, I'd like to now use scientific notation and maybe some properties of exponents to multiply the two numbers here. Okay, the first step is going to be, let's rewrite these values using scientific notation. The first one is going to be 1.2 times 10 to the 7th. That's because there's 6 zeros. You have to go one further to get between the 1 and the 2, so 1.2 times 10 to the 7th. And I'll do the same thing for the other number. This is going to be 5 times 10 to the power of 6. There were 6 zeros, and then we could end up right at the 5. Now, if we want to multiply these two numbers, we can multiply in any order that we'd like. So I'm going to rearrange things. What I'm going to do is I'm going to multiply 1.2 and 5, and then I'm going to multiply 10 to the 7th and 10 to the power of 6. So I'm going to compare things that are similar to each other. So let me rewrite this problem as, okay, it's 1.2, and I'm going to multiply that by 5. And then in the other set of parentheses, I'm going to multiply 10 to the 7th and 10 to the power of 6. So again, just comparing similar parts. It's easy to multiply 1.2 and 5 together, just the numbers that appear in front of the scientific notation. 1.2 times 5 is 6. I won't even put any parentheses around that. That's just one number. Now, in the second set of parentheses, I have 10 to the 7th, and I'm multiplying that by 10 to the 6th. We had a property of exponents that said if the bases are the same, you can simply just add the exponents together. So 7 plus 6, and that is going to be 10 to the power of 13. So I'm going to put that in place of the parentheses here. Okay? So this number is 6 times 10 to the 13th, and I think I'll write it back in that standard notation of, we're saying we're multiplying these two things together. Let's write that as 6 times 10 to the power of 13. Now, we don't have to write this out in a standard way. I do know it means that we're taking that decimal that appears after 6, and it's going 13 places to the right. That would take a while to write out, and it's much shorter and quicker to write it this way. Maybe the last thing to check would be, okay, I'm saying my value for a is 6. Okay, that's fine. That's clearly between 1 and 10, so that works there. And this is the answer to the problem by multiplying these two numbers together. And for our last example, same idea. I want to use scientific notation to simplify this down to one number. So we're not just multiplying here, but we're also dividing in this question too. So I'm going to take the same approach as last time, where I'm going to take every number that appears and write it in scientific notation. So for the first one, that's going to be, so here again we have 1.2. And if I count the number of zeros that appear, there is 9, one more is 10. So that's times 10 to the power of 10. If I look at the next one, which is 3,000, that's going to be 3 times 10 to the power of 3. And I'm dividing this by, okay, here we have 6, and that's followed by 6 zeros, so 10 to the 6. So at this point, I've just rewritten the problem in scientific notation for each portion. And just like last time, I now want to compare similar parts. So I'm going to take the numbers 1.2, 3, and 6, and I'm going to write them together. I'll multiply these two and divide by 6, and then I'm going to compare the powers of 10. I'll multiply these two together and divide by my 10 to the 6. So it's really just now setting it up. So let's see, I have 1.2 times 3, and then I have 10 to the 10th times 10 to the power of 3. This is being divided by, okay, we have 6 over here, and then I have 10 to the power of 6 here. So I'm comparing the numbers and then the powers of 10. So this portion's pretty simple. It's just a matter of multiplying 1.2 and 3 and then dividing by 6. So if I, maybe think about that over here, 1.2 times 3 divided by 6. Well, what is that? 1.2 times 3 is 3.6, and 3.6 divided by 6 is 0.6, okay? So for my first part, I'm going to replace that with just 0.6. Now I have to figure out what's going on with this part here. I'll do that off to the side too. So let's see, I have 10 to the 10th times 10 to the 3rd divided by 10 to the 6th. So for the numerator, it's just like the last problem where I have 10 to the 10th and 10 to the 3rd. I know it's 10 to the power of 13 divided by 10 to the 6th. Oh, okay, now that I'm dividing two things that have this similar base, I'm going to subtract the exponents. So that's going to be 10 to the 13 minus 6. Yeah, if you multiply, you would add the exponents, but if you divide, you subtract the exponents. So this is going to be 10 to the power of 7. So I'm going to replace this entire portion here with 10 to the 7th. Okay, so that's 10 to the power of 7. And okay, I'll write it in our more familiar notation of 0.6 times 10 to the 7th, and I just have to ask myself, well, am I done? And there's a problem here, and the issue is this. The 0.6 should really be 6 as opposed to something less than 1. So the question is, okay, I want this decimal to move one place over to make this thing 6. But that's going to change the exponent here from 7 to something different. Okay, so to figure this out, I think I'll add an extra step. So it's like, well, what does this exponent have to be? So my approach is going to be, all right, I'm going to write 0.6 as 6 times 10 to the negative 1. So I'm just replacing this portion here with what it is in scientific notation. 10 to the negative 1 means you take 6 and you go one place to the left. And then I'm just going to copy down the previous number, which was 10 to the power of 7. If I now add those two exponents together, that's 6 times 10 to the power of 6. And that 6 came from, we had negative 1 plus 7. So now we're all set. This part here is the final answer to the problem. So again, the whole approach was write every number in scientific notation. Then it was compare similar parts, simplify those numbers down, and use some properties of exponents to get a final answer.